Good morning, and thank you for joining me for this presentation. So my name is Luca Canali. I'm a data engineer at CERN, where I work in the Hadoop Spark service and database services. I have a few years of experience with databases, and more recently, in the last few years, also big data and Spark. And particularly enjoy working on the areas of performance, architecture, tools, and internals that I'll be talking about today. And I also like to learn and share with the community. Here are some links that you can find some material at. So I work at CERN, and CERN is home to the Large Hadron Collider, which is the largest and most powerful particle accelerator. And it's also home to 4 large experiments that exploited seeking to further the knowledge on fundamental physics, in particular particle physics. So high energy physics and LHC-related experiments are very data intensive. So data processing is key for the analysis and the success of the entire chain of the experiments. And here in the slides, you can see some of the numbers that we have at the moment. So we have data being processed at petabyte scale per day, and million cores, and about hundreds of petabytes of data already stored into the system. And the computing model for this type of data analysis has been developed about a couple of decades ago and has been evolving since. So for the purposes of this presentation, and to give you an overview of where we stand before we get to the actual core of the presentation, I've divided data at CERN into 3 major chunks. I mean, there are more, but this is for today. So this is a physics data on the 300 petabyte scale, and it's an exabyte problem in terms of computing. Then there is more like the big data, so where we operate, for example, with Spark and Hadoop. That's more on the order of 10 to 20 petabyte scale. And we have applications, for example, for analytics, for accelerator controls, that has been actually presented at this conference last year. And monitoring use cases, analytics, and exploration also of use of Spark for high energy physics. And then we have relational databases, which are part of this presentation. It's about 2 petabytes of data altogether, with one large database for controls that takes about a petabyte, and the rest on several databases. I mean, a large database will be between 1 terabyte and 100 terabyte typically. I mean, you normally don't get to very large scales, except we have one case of almost 1 petabyte. It's also used for physics data analysis, but that's more like the metadata. So that's a tiny bit of metadata that you need to make sense of the large hundreds of petabytes that you have. And then more general use cases on administration and general purpose. In terms of where we run a Spark at the moment, we have Hadoop clusters, so about 2,000 physical cores and 15 petabytes of capacity. And we also have Spark on Kubernetes, as I started this year, and you can get more details at this conference at the presentation that I mentioned in this slide. And I also mentioned in this slide some of the clusters that we have for production, so that you get an idea of the scales where we are. And so let's get to the core of this presentation, the motivation. I mean, actually, the idea for this talk came to me in the springtime when I was contacted by somebody who was doing a survey, asking a few people working with databases, what are 3 tools that you find most useful and you would like to recommend to people for doing database workloads? So I suggested a couple of tools for command line administration and also graphical administration, and then I thought a 3rd tool, or anyway, something that I use often and I would recommend people to use, and I thought Spark. And I said, well, maybe I should actually put some more context into that for the community out there, especially people doing databases, either DBAs or developers, on the value that moving into big data and using Spark can be. And so I represent this with this little drawing here. So one can move from basically databases, and where there are more traditional roles like DBA and dev, and then on the other side we could have big data, and with Apache Spark being a tool very popular for that. And in a way, I mean, you can combine the two, and in terms of the people side of it, it's basically data engineering. So it's no more like DBA, dev, or big data, but it's just a data engineer that can actually use both tools. And it's also the story of the learning experience that we have at CERN, where we started our Hadoop and Spark service with the core people that actually in the database group, with the core people that have database experience, and typically a senior DBA, so at least the 3 of us, There are also, of course, resources that have started more recently. They don't have this background. But some of us have, and I really have enjoyed and given value to the service. And also another slide on the goals. Actually, my real goal here is that for many years I've been going to DBA's conferences and enjoying it and meeting really great people and learning a lot. And I see that some of these people also moved over to conferences on the big data, for example, on Spark, etc. And I would like to entice more people to come, so it's more fun. And so for that, I would like to focus on the value that the tools for data scale can bring to RDBMS workloads, and also the value that people with experience in, say, more traditional data management tools like databases can bring. And then I will have some reasoning about the performance part and instrumentation. And so I currently live in Switzerland, so I thought this analogy makes sense, at least to present at this conference, of analogy of Spark and a Swiss Army knife of big data, also not original. I actually could Google it and find that somebody else had already said it. That's actually key anyway. So why the value of Spark? Because there are, of course, other tools that do specific things that we're going to talk about today. But the thing is that Spark can do a lot. And so you can use it for many different workloads, and I will come back to that. And so you will have data extraction and manipulation, a large ecosystem of data sources, an engine for distributed computing, runs SQL, streaming, machine learning, and more and more. And then different people can use different parts of it, more than one. And so yeah, one tool that also many industries, even in research, we find different types of research, high energy physics, astrophysics, biology, using Spark. So building a community becomes a great part. And the analogy goes on. For example, I mean, there are little bits and pieces in the Swiss Army knife that sometimes you wonder what they do. They look cool and you don't know. And this also happens in the Spark code, I guess. But okay, I'm digressing. Let's get back to our problem today. That's a very simple and long-standing problem. So I have data in a relational database, and I want to run reports. So what happens with the relational databases? For example, this is an architectural diagram of something that we run. It would make sense if you have, for example, some DBA background. So this is specialized rack cluster of Oracle with specialized storage, and all built up for high availability and high throughput of the transactions. What happens is that you pay a premium for all this. And so a transaction is your key workload. If you want to run reports on top of that, you can, but this might cost you. So, and then you can build a hybrid transactional system so they can do reports and transactions well at the same time, but the cost performance is going up. So a traditional thing that people have been doing for decades is that to move some of the data into a system that is optimized for capacity, and so you will spend less for your reports. So in this context, this will mean, for example, we take our queries, instead of running that on the relational database, we just move the data into another system. In this case, could be Hadoop or a cloud storage if you want to do a different, slightly different architecture. Then you can have a tool like Spark that can run the queries for you on top of it. All very simple. And so how can we do that? And for example, with Spark, of course, we can read from databases. We have the JDBC data source, and we can read the database. It's all very much straightforward with a data frame infrastructure. There are also some additional optimization that you can use. For example, the fetch size is a typical one for all databases. And there are also specialized optimization that you can use, for example, for Oracle. This is Spark, an improvement, a PR that has been put in that actually improves some workloads for Oracle. If you have to move a small amount of data, this is all fine for you. If you have a more complex problem, you might run into issues like the fact that an important amount of CPU is consumed when moving data from the database into another system. This also depends on the source database stack. And for example, if you have tables with short rows, typically it's challenging. And then you have to take care of the parallelism. For example, you want to have parallel extraction so you can go fast, but not too fast so that you overload your target system, which then you're back to your original problem. So there are tools that can help you for that. For Apache Scoop is a very popular tool that you can use for extracting data from relational databases. It works for many databases. It has an Oracle connector with specialized optimization for Oracle. And we use that regularly to schedule jobs for our users to move the data into HDFS, effectively building a data lake where they can run queries. Scoop import job would look something like that. If you're running, for example, on Oracle, against Oracle, and then you have optimizations, this direct optimization, that, and also the chunking method. It's some pretty clever code by people who know Oracle that have been put into that. Of course, Scoop works also from using other databases, and it does optimization for those. Okay, once you do data movement in bulk, you can also, then you're building a data lake, and there are also other ways, of course, where how you can put data into this data lake. Streaming is very popular these days. You can stream data, and we have in our user community some workloads that indeed use the streaming, and then they end up in the same Hadoop cluster, and they are also queried using Spark and SparkSQL. Okay, so then you move the data, and then another important dimension here is the data formats. Columnar data formats are particularly suitable for reporting because they have features like column pruning, compression, and encoding. And also partitioning and bucketing are also quite important. There will be a presentation after this on bucketing. But let's just see somehow how probably is familiar to several of you or have already used Spark, how these optimizations in Parquet, but also available in other common format like ORC, can be used for the performance. There will be partition pruning. So if you have multiple partitions and you select on a partition key, of course, you just need to read a chunk of data, and then you will have also optimization like filter push down. They can use also the statistics that Parquet is using. For example, if you're querying a value for a value that is greater than the maximum value of a column, Parquet will know immediately that no results can be returned, and so it will be very fast. And of course, column pruning, it's an obvious one for columnar formats to save on I/O. For me, the learning experience for all this has been that I needed to see more how this worked. So I figured out a couple of tools that are available in the open source to actually go and dig into the metadata. I put also here a link on some notes that I wrote when I was looking at this. So really going and looking on the metadata on some data that you know and you want to explore helps you to understand how this one works. And at least for me, this hands-on feeling was kind of important. Okay, then you move the data. You have a nice data format, and now you want to put the SQL on. That was the whole idea from the beginning. And here Spark indeed is super useful, and SparkSQL and the dataframe API are powerful engine that are going to help you to run your queries on the offloaded system. And then, of course, the features that I already mentioned will help you, and the fact that SparkSQL has code generation, and these days there's also a cost-based optimizer, and all this builds a very nice infrastructure. Of course, the ecosystem is rich, the competition is there. We also tested Impala and Presto, but I already mentioned some very good features of Spark in general as an ecosystem that makes it a very good choice for this. And of course, there are many interfaces that people can use, and okay, this can be an extra, say, bonus, but also some learning experience coming into this environment, because people might want to use PySpark to access this, or Spark Shell, or they want to write jobs, or use notebooks. These days are very popular. We have a web-based notebook service at CERN called Swan. It integrates Jupyter, and then people run queries there, and then use the Python APIs. They will be able, for example, to make graphs out of it. This is from monitoring data that they are examining. In terms of lessons learned, something that came new to me when running queries on this offloaded system using Parquet and SparkSQL, for example, is that queries that I expected to be I/O bound became CPU bound, as Parquet is a very optimized format, and at one point is very much CPU intensive. So much that I ran some micro benchmarks, and I figured out that on a server with 20 physical cores, I could at maximum have a throughput of 3.4 gigabytes per second reads because of really the large amount of CPU consumed by Parquet. I mean, this is a high throughput, but somehow you see a query that was I/O bound on your original system, row-based database, and becomes CPU bound. But the nice thing here is that you can scale it up, and CPU on, say, a big data system will cost you, let's say, less in terms of, for example, licensing, and will be an easier way to scale rather than a proprietary database. Linking also to the previous talk, something that we find very useful is also to do benchmarking SparkSQL. So I can probably go quite quickly on this one and refer to the previous talk and the use of the benchmarking tool TPCDS is quite useful for stress testing, understanding, for example, the monitoring infrastructure, understanding how the system works at scale. TPCDS Benchmark, for example, can be run. This is a run, that was run at 10 terabyte scale. And the lessons that we learned here is that basically we could capture, for example, some misconfigurations in the new systems that we commissioned at one point using this benchmarking infrastructure. Another thing that for example, we figured out is that TPCDS queries, they use a lot of shuffle and they're very intense on that. So using local SSDs for shuffle is a very good idea for performance. So now when we provision machines for that, at least on the Hadoop cluster, we have local SSDs for the shuffle areas. Also, we figured out some improvements and regression on TPCDS, but again, this was covered in the previous talk. In terms of learning experience, also SQL, I mean, it's super old, but as a technology, but there are new things that one can learn, I think. And the first time I approached Spark, I saw that I could write SQL as I've been doing it for years, but there was also another way, basically, with the data frame operation syntax. But at the same time, what is important to realize is that the two are the same. Basically, what matters is the relational algebra that's behind it. And so at the end, they're all the same. And if we use execution plans, again, a very old, say, technique for all database workloads, we can figure out that the two queries, if they are written in SQL language or data frame operations, they end up in the same execution plan. Okay, so that's it about the learning experience on basically moving from database into SparkSQL and Hadoop, and something about how performance and techniques, performance tuning and troubleshooting and techniques from databases can actually be brought over into the world of Spark and big data processing. So instrumentation is key for basically big data, for any data processing. Okay, Spark has already quite a large amounts of tools for performance monitoring. Some of them are pretty much standard, and like the web UI is part of the product. And if you use Spark, you should know about it. Otherwise, you can go and experiment with it. One thing that I would like to point out is that Spark, at least in version 2.1, has quite well-developed system of metrics that you can use to instrument your workload. And these metrics basically record whatever happens on the task execution, and then via the listener bus, they report it back to the driver, and the driver would take care of that for the web UI. And if you're setting up the event log writing for the history server and also other tools that can read it, they will be written there as a JSON file. You can also write your own plugin to the listener interface, getting these events that come with the Spark metrics. For example, I've written a small tool that you can use, and I've linked here. And, but the main idea is that you have these metrics, and these metrics will help you to understand what your workload does, so you can use them to instrument what is happening. I mean, this is something, instrumenting the code with metrics on the execution of a data engine. It's a very, say, old technique, And I think we should also carry this one over into new tools like Spark and all the big data processing tools. These are some examples of the type of metrics that you have. You can have the executor runtime, CPU time, then metrics on the garbage collection, IO metrics, shuffle metrics. It's now in the Spark documentation after this ticket, this pull request. Actually, there is a second metric system in Spark that allows you to dump metrics into an InfluxDB or other sinks. There is a list of them using the drop wizard metric system. You just configure like this. And then you can build dashboards with Grafana where you can have, for example, the number of active tasks as a function of time, the CPU, and also all the task metrics that I mentioned before are also now available in this other metric system that can sync data into, for example, InfluxDB or other sinks like JMX. This is very important because, for example, if you can see the number of active tasks as a function of time, you can see if your job is efficient or not. For example, here, this peak, okay, it's barely readable, but it goes to up to 500 active tasks, but then it drops for a while. So we have 500 cores here, but we are not using them all the time. So we can investigate why. Maybe it's a straggler, maybe it's a skew in the data. It's something that we need to investigate. A third point quickly is that now we have a tool that has worked well in at least in one case, moving data from relational databases into a data lake for scaling up reports, and then some ecosystem that has been built and some metrics that we can use to measure the data. So we want to use it for more and scaling up our workloads. A couple of things that I will briefly mention that we are now working on are, for example, are using Spark for physics, with the same infrastructure, but now attacking a different set of data that was not possible to process with relational databases because of their size. And for example, physics data, we took 1 petabyte of it, which is just a small chunk of the 300 petabytes that are available and more. And then we use a pipeline that is using Spark to produce, for example, this is a data reduction workload that basically selects on a columnar data format, which is the format that is used by physics. It's similar to Parquet, but slightly different. There is a talk at this conference that describes it. And then we use Spark, and we can filter the data and produce histograms, for example. This is very similar to the previous workload that comes from relational databases, similar tool, but a different type of data. And another one that now we can do is also machine learning at scale. Again, take physics data and use Spark for feature engineering. There again, we can use, for example, a dataframe API or apply some UDF into the data. So basically carrying over methods that have been developed before. And also we can do hyperparameter optimizations and feed the data into deep learning tools. And finally get, for example, a classifier for a particle. So we've been able to implement all this pipeline basically using the same tooling and the same systems that were used for the previous system. Okay, so now wrapping up on and getting back to the main theme of the presentation. So that's if you come from DB, DBA or Dev, and move into Spark, you'll find familiar ground. So SQL, cost-based optimizer, execution plan, hints, grouping, partitioning, that will be all there. And at the same time, you'll be able to basically use and take your experience on performance troubleshooting, instrumentation, SQL, and make them to good use for the new system. There will be a learning curve coming from a database because several things are different in this environment. For example, the environment is more heterogeneous in terms of usage. You will have Python, Scala, Java, notebooks, and all varied different, environment that you have to support. And also, there will be differences. I mean, dataframe API is basically SQL and tables, but there are some differences that you will have to understand. You have to understand data formats. But the thing is all worthwhile because what happens is that you increase the value of your system and also the things that you can do, because Spark can easily scale up your SQL workloads. So once you move your data from, for example, the database source into the into a Hadoop system or a cloud storage, and you use Spark SQL to query it, it will be quite easy to scale it up and so run jobs with large amounts of cores and CPU to process it in a small amount of time. You will also be able to run more workloads. So you will, in these systems, as shown very briefly in a couple of examples, we've been able, for example, to process high energy physics data using a pipeline that more or less was built for a data lake for offloading queries from databases and other queries of that kind. So more data will be accessible to you. And another very important point is that Spark has, of course, a quickly growing and open community. There are nice conferences like this one. And the community is open also to proposals and to implement new features. I mentioned a few pull requests that were nicely addressed by the community, and help was given on putting these new features, for example, for performance instrumentation into the main product. So the conclusion is that Apache Spark is useful and versatile. And if you're doing databases, it's a nice tool to add. And also, if you're doing databases, you have value to add in terms of experience, for example, for performance tuning and also practices on SQL, say, troubleshooting that can be carried over into this environment. And with this, I would like to conclude the presentation, and thank you very much for your attention.
All right, any questions?
So thank you for your talk. I'd like to ask you, how do you use the metrics in order to improve the performances of your Spark jobs?
How do you use, sorry, what?
The metrics. So you collect some metrics?
The metrics, yeah.
Yeah.
So, for example, the Spark metrics, so the executors send metrics to the driver, and then we can collect them. And as I said, we have things like runtime and CPU time and garbage collection time. So, for example, suppose, and you can aggregate them over, for example, your SQL execution. Suppose, for example, you have a CPU-bound workload, you will have the runtime equals to the CPU time. Suppose you have something that suffers from a lot of garbage collection, you will see these metrics, JVM ZC time, going up. So maybe then you think, okay, maybe I need to add more memory. And similarly, you will have IO metrics and shuffle metrics that you can that can show you that, for example, shuffle is taking a lot of time. Also, there is the time of the shuffle. And with this other metrics system, so the previous one is this the Spark task metrics, and this one is it's metrics that are sent, for example, for eventually to a Grafana dashboard. For this one, you can see how for example, with the first graph, how efficient the computation was in terms of using the available cores. And if you find that at one point the number of active tasks goes to a very low number, then you have to start drilling down on why this was the case. And okay, for example, looking at the execution on this particular point in time to see if there was a straggler job. For example, if the small amount of active sessions was because there was one session running on a machine that was particularly slow. We had this a couple of times using old machines. This is the type of troubleshooting you can do.
Okay, so mainly it was like manual, not automatic. So you didn't.
This is mostly manual, yeah.
Oh, okay, thank you.
And there are also other tools that attempt to, for example, read the event log and produce some recommendations. But in this case, it's manual. Hopefully, we'll see more in the future in terms of performance troubleshooting and automating it.
Hello, thank you for the talk. I was interested in like Large Hadron Collider. You would have petabytes of data, and you can't run that experiment like again and again. So how do you capture data provenance, and do you use Spark for that? Could you?
For the no, that's at the moment, no, that's something we don't know much about it.
All right. One last question.
If you have time. My curiosity is related with moving from relational databases to HDFS and Parquet. Do you try to experiment with different databases like Cassandra, CockroachDB, or, you know?
As a source, you mean?
Yes, as a data source. I'm interested why some people choose HDFS. Because we have like Cockroach, which is a new SQL movement from Spanner, but why you have chosen?
As a destination, okay, right. Good question, yep. I think going back to the whole idea, I mean, the main idea is to take data out of a relational database and put it into some system where you can run queries with another engine that could be, for example, SparkSQL. At this point, this has been done a few years ago, where Hadoop certainly used to be a kind of trendy for all these data lake type of activities. But you can replace Hadoop here with other types of cloud storage, for example, or other systems. There is no necessity to have Hadoop. The thing is that Hadoop comes with Yarn as a cluster manager where you can run Spark, and it comes with a file system, but it's not the only solution. This architecture in this diagram can be done with another solution replacing Hadoop with something else.
All right. Thank you, Luca.